Dunjko from Leiden University, talking about speedups. Okay, let's hear it.
Yeah, so thank you very much, Barbara. And first of all, I'm deeply grateful to the organizers for giving me a chance to participate at all, and especially to talk to you guys about this problem. So the topic is quantum speedups with smaller quantum computers. And this is sort of a bit of a strange question that we've been thinking about for a little while, cooking at low heat, starting while I was still at Max Planck with Ignatius Sirac in 2018. And we still have a little results dripping that I'll tell you about in a second. So we started with a basic motivational question. And it's like, suppose you're given a computational problem, and let's for concreteness say a satisfiability problem. So you're given a boolean formula over n variables, and you have a quantum computer which can only handle k qubits, and where k is significantly smaller than n. So we wanted to know, like, does it really help to use the quantum computer at all? Is it any good? So here, I don't want to get you on the wrong track thinking about SAT and quantum computing just yet. Let's assume the quantum computers are really good at SAT, but still it's not clear whether it's going to help. So on one hand, the intuition says it should, right? If it's a faster device, even though it's smaller, you should be able to use it. But if you, for instance, think about factoring, and I give you like a challenge to factor 1024-digit number, and you have a device which can do this in one step, but when the number is bounded by 128 digits, it's not really clear that this will help you at all in any significant way. So this was sort of our basic question. And I somehow don't want to go too much into the motivation for this question. I would feel like I'm preaching to the choir at this conference, but of course, we're all trying to get around limitations of real-world devices which may be available in the next few years. And here, today's talk, a small disclaimer, is in comparison to other talks that we've heard, gonna be a little bit in la-la land, in the sense that I will not be considering any errors, and my algorithms are in fact gonna be quite deep, and I will not be thinking about that. I will just be focusing on size issues. And my starting point, in fact, will not be whether I can get a device to do something useful. I will be assuming that I have a device which can, at least for some instance sizes, beat classical performances. And moreover, I will not necessarily think about supremacy type statements, but just speedups, maybe quadratic speedups for interesting problems. So let's stick with basic curiosity about the first question that I posited. So how would you handle this question of what to do with a k-size quantum computer given an n-size problem? So like three things you can do. You can somehow hack it. You can simply look at a popular algorithm for your problem, and you can see whether there are any small subroutines which are just the right size for your quantum computer, and then speed those up. And in practice, this is probably the way you would do it, and probably the best way to actually get a real world speed up. Or you could try to be a little bit more systematic. For instance, you could come up with a quantum algorithm for your problem, then look at the quantum circuit, and then somehow partition it into smaller sizes, and maybe use a large classical computation to help you out when you're lacking qubits. And this was done in a series of works by Bravi and Smith and Smolin already in 2016, and Peng et al. More recently. And here we're going to be doing something similar, but on the side of classical algorithms. So you're going to start with a classical algorithm which somehow chops well. And then when the instance becomes small enough, you're going to quantum enhance those. And there will of course be trade-offs in which method would be the best for your particular case, but I will focus only on this third part here. So the setting in more detail, I will have some classical algorithm in mind for some particular problem. Specifically, I'll be thinking about Boolean satisfiability and the algorithms of Schöning, PPSZ, DPLL. If these names don't mean anything to you, it doesn't really matter. I will introduce whatever I will need at a later point. I will also be thinking about Hamiltonian cycles problems and the algorithm of Eppstein. I will assume that I have at least in principle, a quantum algorithm that does better than those classical algorithms for the problems at hand. Here I will have a few options. I will assume I have an n-sized instance. The size here, the best thing is to think about Boolean satisfiability, and the size of the problem is sort of the solution space size, which is the number of variables I'm working with. My quantum computer is smaller. And at this point, I want to ask, so when does the quantum computer genuinely help? And here I have to start making some choices. And the choice we made was we're going to be interested in polynomial speedups, and in the standard asymptotic sense, in a complexity theoretical sense. So for these types of problems, these problems for NP-hard problems, the exact runtimes are typically exponential, and they can be written in the form of 2 to the gamma n, where this gamma is some prefactor sort of determining the actual speed of my algorithm. And what I'm interested in starting with an algorithm which has some gamma c constant, which is dictated by the classical algorithm, and then reducing it by some constant value. And this is immediately a polynomial speedup over the original algorithm. And off the bat, you can notice that this imposes some restrictions on reasonable questions, like, for instance, k certainly cannot be constant. Recall, k is the size of my quantum computer, because if it's constant, then I can simulate it in constant time, right? And logarithmic is not going to be good enough. So the most interesting cases are where k is actually proportional to n, but smaller. So I'm going to introduce a constant alpha, which tells me just how much smaller my quantum computer is than the classical, but both will scale in the setting that I'm considering. So the method that we propose is something we call a hybrid divide and conquer. It comes from the observation that there are classical algorithms that naturally fall into smaller parts, like algorithms which employ divide and conquer strategies, or algorithms which are recursive, or so-called backtracking algorithms, also have this feature that within the run, you're somehow simplifying the problem and running it in a smaller instance. And please always have in mind the picture of the problem of solving boolean satisfiability problems, where I have clauses which constrain the possible settings of, let's say, 3 bits in 3 SAT in a weak sense. So 7 out of 8 configurations are going to be fine, but I still have many conditions that I have to satisfy simultaneously. And in this case, for instance, backtracking algorithms would generate something that I'm going to call search trees. So they're going to be trees where each vertex denotes a partial assignment. Right, so it's a proposed assignment, and when I set the next variable, I bifurcate into the next 2 possible nodes in my graph. So this is exactly what it is in the case of backtracking algorithms, but I can also think a little bit more generally. These nodes could be more general objects, like subcalls to some subroutines that my algorithm might utilize. So this is what I mean when I say a tree. So the hybrid method is going to be as straightforward as can be. You pick your classical and quantum algorithm. You run the classical algorithm until your problem shrinks enough, and when it's small enough to be fit in your quantum computer, you run the quantum computer, and that's it, right? So it's really not very deep at this level at all. The classical algorithm tells me how I split the thing. The quantum computer can run whichever algorithm you wish. They can be completely distinct algorithms, or in principle, the quantum computer could run a quantum enhanced version of the classical algorithm. And then I'm interested in expressing the complexity of the overall process. This hybrid method is a function of k and n, which are the sizes of the quantum and classical machine, so the instance in the quantum machine, and the corresponding complexities of the classical A and quantum algorithm B. And of course, the catch is going to be that you will fail to get asymptotic speedups for a number of not completely, maybe off the bat, obvious reasons. I would like to talk more about quantum algorithms and NP problems because I think it's a very interesting topic. I don't really have the time for it, but let's just say the following. We don't believe quantum computers can solve NP-hard problems in polynomial time, but they can still help a lot. So we can essentially quadratically speed up most worst-case algorithms. We have interesting suggestions for approximation algorithms that we've heard about in the talk before, and we'll hear again. Quantum computers may offer interesting heuristics, so algorithms for which we don't have good guarantees in a theoretical sense, but maybe practice will show that for important instances they work well. And what I want to point out that generically, quantum computers either help in the sense of being an enhancer of a classical algorithm or provide a genuinely new approach. And I want to think about enhancers, right? Because then whatever the classical community has figured out about classical heuristics, I sort of can import that knowledge into the quantum domain and not necessarily have to do as many numerical tests as you might want to do. So how would this work ideally? To give you a little bit of a flavor. So suppose we're going to solve a Boolean satisfiability in the most naive possible way. So I'm going to do a brute force search. So I'm going to choose each variable, and my tree is going to branch into the situation where I chose it to be 0 or 1. So that's my classical algorithm. My quantum algorithm is the quantum analog of brute force search. So it's going to be Grover search. And in this case, my tree is really going to be a full tree. Complexities are simple. In the classical case, it's just 2 to the n. So my gamma rate for the classical algorithm is 1, and the quantum is 2 to the n half because I get a quadratic speedup. And if you do very simple math, you see that the hybrid runtime picks up a nice format in which you get 2 to the exponent, which somehow smoothly interpolates between the classical runtime and the quantum runtime with the corresponding weight, which is determined by the ratio of the classical computer size, instance size, and the quantum computer size. So this is, of course, for brute force search, but you can show that it holds more generally for algorithms which somehow come from, whose runtimes come from standard occurrence relations. And you always get this nice shape that the hybrid runtime is governed by a quantity which is somehow interpolating smoothly between the classical and quantum runtime. Okay, it doesn't work always, of course. I will show that generically actually it fails for some reasons. But what I want to point out now is that at least in this picture, this gamma hybrid value, which tells me about the speed of the hybrid approach, is always better than the classical one, no matter how small my alpha was. So no matter how small my quantum computer is relative to the instance size, I always win a little bit, a small polynomial improvement. And when this happens, we call this a threshold-free scenario. So we're kind of interested, when is this ever possible? And just going back a little bit towards why would you care? Because this allows you a free control of trade-off between the problem sizes you want to handle and the amount of speed up you actually want to attain. And it can fail for essentially two different ways, the reasons. One is because your algorithms require too much space, specifically the quantum algorithms, in which case you get no real speed up. I will say what I mean by this in a second. Or because your search trees are of an inappropriate shape. And in the second case, you will only get speed ups when your alphas are really high. So it's not a threshold free setting. So let's look at this for a second. So in the case of problem with computational size, the issue is that I pulled a small sleight of hand in my computation of this expression here, which talks about the speed in terms of interpolation between classical and quantum runtime, in that I said that I start my quantum computer when the instance becomes of size k. So k would be alpha times n. That's what this equation essentially says. But note that k is really the size of the formula I can handle in the Boolean satisfiability example. But the size of the quantum computer is generically larger than that, right? It is governed by the quantity, which is the space complexity of my quantum algorithm. And in the simplest terms, if it's f of n, the space complexity, then the size of the formula I can handle given a quantum computer of size alpha n is f inverse alpha n, not alpha n. So for instance, if my space complexity is n squared, then the effective size I can handle is square root alpha n, both alpha and n, not just alpha. And if I do the math with this, I see that my coefficient with the quantum term in my speed actually starts decaying as my instance grows. So it's not a polynomial speedup in the limit. It's super linear, but not a polynomial speedup. Not what I want. So this says that the space complexity of my quantum algorithm should be essentially linear, and that's a very, very stringent constraint. To give you an example of how bad trees come into play, we'll see this more later on. But classical algorithms do better than just brute force search. And at some points, for instance, they can figure out that certain variables have to be fixed to some particular value, and then a parent has only one child, right? And the algorithm is from that point on much more efficient, maybe linear, maybe polynomial in time. So if I can only switch on my quantum computer later on in the game when my problem has become very simple, it actually has no hard work to do. I'm using it in the regime when the runtime that remains is just polynomial. And the hard work was already done by the classical device. This yields no speed up in the end. But if my threshold is higher, like if my quantum computer is comparatively larger, then I can get it to use to be active in this exponentially hard regime. So when does it work? It's actually quite easy to characterize this in a very, very broad sense by using something we call the tree search tree decomposition. And credit to Matisse Ranella, who kind of pointed out that this is a nice way to represent it. So once I fix a classical algorithm A, I have some search tree defined. And together with a quantum algorithm B and a size limit alpha n, I can somehow figure out in my search tree when will I be able to switch on my quantum device. So we'll get a search tree T sub 0, the blue region, where I have to use the classical device. And I will have a bunch of subtrees dangling at the leaves of T sub 0, where I can use the quantum device. I'm going to call these trees T sub j. And then it's not difficult to convince yourself that if the following is true, then I can get a speed up. So I'm going to assume that the entire tree is exponential in size. I can relax this, but I don't want to. And the hybrid approach will achieve a polynomial speed up if the following two conditions are met. If the average time taken by the classical algorithm on these subtrees T sub j is polynomially smaller than the average time of the quantum algorithm. And second, if a constant fraction of these subtrees T sub j is itself exponentially sized. And the intuition should be very clear. So I'm insisting on exponential trees because then I don't have to care about overheads and fine grain complexities. And conditions 1 and 2, well, 1 tells me that the quantum computer should actually be faster once I use it. And condition 2 guarantees that the quantum computer will still do some of the hard lifting. And both conditions 1 and 2 can be contingent on what alpha is. And if the family of trees is such that it's not, then it's a threshold-free scenario. And we have a couple of versions of this theorem, but this is sort of the most general one. So now, this was all not particularly deep, but maybe illustrative. I want to tell you about what we figured out when it actually does work. So these are going to be a sequence of examples where we could make the quantum algorithms sufficiently space efficient without sacrificing speed while maintaining reversibility. So that's actually achieving reversibility. And the very first example was in the first paper that we did. We tried to quantize Schöning's algorithm for set solving. It doesn't matter how it works because we failed. There was a problem with that, but then we figured out that there's a derandomized version of the same algorithm, which reduces the problem of satisfiability to another problem, which is called PromiseBa SAT. So there, you're interested in the following question. I give you a formula and a satisfying an assignment of all the variables, and I ask you whether there exists a satisfying assignment within L distance from your starting point, from your assignment X. So L distance with respect to the Hamming distance. That means you're allowed to flip as many as L bits from the starting assignment. And now the randomized Schöning somehow splits the search space into these balls and then runs PromiseBa SAT on each one of them. And if you solve this PromiseBa SAT naively, you get a ternary search tree, because what you do is you check each clause and which is not satisfied, and then you know that if you flip one of the 3 bits, it will become satisfied, but you don't know which one. So you somehow try all 3, right? And this yields your tree. But for us, this yields a problem. Because note that in the end, I have to somehow always keep an eye on which variables have I flipped all along. And since I have L variables that I can flip, and L is somehow proportional to N, and since I need to store the indices of the variables, and I have N variables, so I need log N bits for that, this is N log N, and this actually constitutes too much space. I need something which is linear, so it doesn't work. But then you can resolve this by noting that, in fact, what we don't really care about lists. We don't care about storing sequentially which variables we flipped. We need to know which ones there were. So we need to store sets, not lists. And sets require less space. So in fact, I can do that in k times log n divided by k. And when n and k are sort of proportional, then this is really essentially linear. But then you come into other problems that the set update is not reversible. If I add a variable to a set, at the next step, I no longer know which variable I've added, and that's somehow bad for quantum computing. And if you do direct reversibilization of the process, then you get something which is exponentially slow. But then we came up with a recursive memory structure. I can tell you later on about it in questions if you would like to see it, which achieves the right space complexity and has polytime updates and queries and everything you would like with the lists. And somehow taking that further, we've shown that you can also do similar things for different types of algorithms, specifically for Eppstein's algorithm for Hamilton cycles and cubic graphs. Again, I don't need to really go into details. This is the part of the story where it becomes, depending on your preference, either very delicate because you have to be very careful with your space all along, and you have to really read the details of the algorithm, kick out everything you don't need. You can call it tedious, depending on your flavor. But the point is, it does work. And what we get is a polynomial speedup, no matter what alpha is, no matter how small my quantum computer is relative to the instance, relative to the best known classical bound. And the speedup is threshold free for all alphas. And essentially, I get to use Grover search because the trees are effectively close enough to fall to win. But this is not always the case, right? So now I'm going to take you into the research that is not fully finished, but we know some results that I can share with you, which has to do with backtracking. So in backtracking, as I briefly described, you're somehow looking at the formula and you're choosing a variable and you're trying to figure out whether you know how to set the value of that particular value. And this is generating a sort of a tree of partial assignments where when a node has 2 children, that means I didn't know how to set it, so I guessed. And when it has 1 child, then there was something telling me that it should be one value or the other. So the size of the tree depends on sort of these local reasoning rules you're using to decide whether you can set a value. And this yields different algorithms. For instance, the so-called DPLL algorithm, which is a very famous heuristic for set solving, uses 2 simple rules, like checking whether the variable is just a single variable in a clause, then you know how to set it, or whether it appears with the same polarity in every clause, then you again know how to set it. And the so-called PPSZ algorithm, I'll say something more about it in a second, uses something which is called S implication, which essentially looks for polynomially provable statements that a particular value should be a 0 or 1. In this case, you can't use Grover search anymore. So the trees can be sparse enough that the number of vertices is less than the square root of the full tree. And the Grover search algorithm somehow will always explore the full tree no matter what. There's no way to make, to stop searching in one probabilistic branch. Luckily, Ashton Montanaro and Ambinis and collaborators, they've come up with a quantum backtracking scheme algorithm, which is based on random walks, which for large instances really achieves a quadratic speed up in the number of nodes you will explore relative to the classical algorithm. Well, you don't really, you do everything in superposition, so it's not about nodes, but it's quadratically faster in terms of the nodes. So now I'm interested in using quantum backtracking if I can. It turns out you can, and it turns out that this allows you to quadratically to speed up, to get polynomial speedups for a broad abstract family of search trees. And these are those which are somehow everywhere dense enough. So I'm going to say that a tree is sort of lambda dense if every subtree of depth larger than a kappa n is exponentially sized. I don't care about the exponent, it's some lambda, it doesn't matter what it is for the moment. Now, if these trees are generated by an algorithm, then in principle, of course, I can run backtracking over it. And if it's the case that that logical reasoning which dictates the shape of the tree, I can do space efficiently, then the entire thing can be done faster using a hybrid approach. So I'm somehow satisfying both conditions of the main theorem by enforcing that the tree is dense enough. And I will not go too much into detail, but from this you can do a leap to a different kind of reasoning that, if my problem is hard enough, I really don't have to be clever at all. So under the strong exponential time hypothesis, I will know that there exists a SAT family where the trees are going to be guaranteed to be as dense as I wish. And then I can always get a polynomial speedup over any classical algorithm. In fact, of course, that's if you believe in the strong exponential time hypothesis. We can discuss later what that means if you're unfamiliar with the term. By the way, this lambda parameter, which is the density, this is also telling me whether I can use Grover search or whether I need to do backtracking. If it's larger than 1/2, Grover will do. If it's below, I'm going to use quantum backtracking. And there's no reason why I wouldn't. And now the fourth class is sort of a painful class because I really wanted to have a positive result here, but unfortunately, we're not there yet. It's the algorithm of Paturi, Pudlak, Sachs, and Zane. And this I like is because it's the basis for the fastest known exact SAT solver at the moment. It has some bells and whistles atop of it, but essentially this is what you do. So in this algorithm, the search tree is built by making guesses or by proving S implications. An S implication is considering subformulas involving at most S clauses, and then you check whether this subformula forces your variable to be either 0 or 1. And this is a large polynomial computation, but it's polynomial. So it's sort of a polynomial size proof. And the theorem, PPSZ theorem, tells you that if you do this, along the path which leads to satisfying assignment, if one exists, you will not have to make too many guesses. You will have to do something like 0.38 n guesses. So the purple ones where I bifurcate, this is where I had to guess. The green ones are the ones where I could prove the value. So we really wanted to speed this up because then you would get a quantum speed up of the best algorithm that we have. But sadly, it doesn't really work. Because this suffers from batch trees. Like the guesses can happen early on, and in this case, the quantum computer will have nothing to do. And you could beat this if you come up with a very space-efficient implementation of sort of these logical steps that the algorithm does, and we know how to do them only for some special classes of formulas. And we kind of think that in general, it can be done sufficiently space-efficient because it would imply that P-complete problems can be done in sublinear space with sub-exponential time. We're kind of skeptical this can be achieved. Or rather, we're skeptical that we can achieve, let's put it this way. Okay, so now I will close essentially the talk with a little bit of theory and some practice, and the theory is going to be very, very shallow. But I have to ask the question, right? So far, everything I've shown achieves a small polynomial speed up over the classical algorithm, right? So you can ask yourself, but can I even in principle do better than that? And I'll give you two very, very simple direct answers. One, in the case that you're starting a hybrid approach, which is really using a classical sort of tree type process to reduce the search size and then runs it in a quantum computer, then generically you will not be able to do better than polynomial faster, even if the quantum algorithm itself is exponentially faster, simply because the top of the tree, the stuff that you run on a classical device, has non-trivial depth and it's generically exponentially large. right? So you can get better than quadratic speedups for certain alphas, etc., but generically not better than polynomial. But can we do better than this? And the answer is sort of yeah, sure. Of course, you would like to use quantum computers also to help you in the top of the tree, and then this is something that we would like to do. But in fact, I can prove that we can do exponential separations by constructing a contrived, well, not a contrived, but a sort of an obvious artificial example, just to show that it can be done. So it's very simple. So take, let's believe that there exist BQP decision problems that take 2 to the exponential time in a classical computer, right? And in fact, they're going to be sort of decision problems over circuits that are promised to yield a 0 or 1 outcome with bounded away probability from 1/2. So under this assumption, for every alpha, there exists a problem family such that the classical algorithm will take the runtime 2 to the lambda alpha n. So alpha is this hypothetical rate of simulating quantum computers. Alpha is the size of my quantum computer, and n is the size of the instance. Yet the hybrid algorithm does it in polynomial time. And I mean, the algorithm is, sorry, the problem instance is sort of, in some sense, it's the simplest one you can imagine. So imagine you have an n size input, and then you have a classical circuit which queries all bits of the input. And based on this, it constructs a quantum circuit of size alpha n and runs this many times, iteratively. It doesn't, as long as everything is done polynomially, the quantum computer will always be able to do this in polynomial time combined with a classical device, whereas the classical computer somehow trivially always hits the bottleneck that it has to compute what this quantum circuit does. So it's as simple as can be. Now, I want to say that, of course, one thing that we kind of care about in Leiden, and also myself personally, I like to time and again think about practical aspects of all these things. So right now we're investigating one algorithm at a time and trying to figure out whether we can get these polynomial speedups. And this is interesting, right? And we know that in principle it can be done beyond just decision problems. You can go to branch and bound type problems, and it's still most likely going to work. But what one should really be wary about and thinking about is speeding up really, well-functioning classical heuristics. Right, I will talk about this in a second, because we're solving NP-hard problems, and we're not going to be running things for an exponential amount of time. And then things become a little bit tricky, right? Then theory starts to break down. You cannot say much about trees. So we have a couple of, or one bachelor student, in fact, who's now studying what the trees from DPL come from. What do they look like in the case of hard random instances, and whether we can get sort of small, very modest polynomial speedups. But down the line, all this is going to be sort of still lacking, because I'm thinking asymptotically, which is not what I really want to do. So what we really want to do in the real world is somehow, heuristically combine classical with quantum algorithms. And we started something in that direction, specifically where we're interested whether we can detect whether a given instance should be handled by a classical or a quantum algorithm. It was a seemingly simple question. I give you an instance of, let's say, max cut, and I ask you whether a QA with some depth will outperform GW on that particular instance. And you can easily see that at least under the unique games conjecture, if we assume that GW is the best approximation algorithm, determining whether it does better or not is itself probably NP-hard. You can tweak the question a little bit to make it NP-hard under the unique games conjecture. So we throw everything into machine learning machinery, and it does quite well. It predicts like with 90% accuracy that things work. And we imagine using this as a subroutine in an algorithm which actually chops up our problem heuristically. And of course, here we can absolutely forget about any theoretical statements. One has to resort to numerics. Okay, so let me give you just a few final remarks to tie up a few loose ends. So I mentioned that I will somehow defend one thinking about NP-hard algorithms. And I think the fully honest statement is because they actually matter, right? So they're somehow shunned in the quantum case because we're not going to get our exponential separation there. But we need to solve NP-hard problems as well as we can, right? They're commonplace in AI. They're all over the place, and AI is something very important nowadays. So we need to find ways of doing it better using a quantum device. There's a second reason, which is sort of more local and pragmatic, and that's since we don't have really smart ways of solving NP-hard problems, we don't have something which does it in polytime, we're not doing much better than search, and our local algorithms can be relatively simple. And because of this, we can come up with quantum algorithms which require less space. So it ends up working because of this particular reason. So we can somehow leverage the brute force against the the clever algorithms, because the clever algorithms are not so insanely deep. Like if you were using some very theoretical deep structures, and things would probably not work out as well. Now, maybe you have a feeling that things are somehow not super optimistic for small quantum computers, but I just want to emphasize that we've made a bunch of choices here to be able to make clean statements, like caring about asymptotics and things that you can prove. This is, of course, not something you will necessarily care about in the next 5 to 10 years. Our definition of what it means to be a smaller quantum computer is sort of as stringent as possible, because we're talking about the instance size. We could have been thinking about the same question, but when we demand the quantum computer to be sort of proportional to the smallest known space complexity for the same algorithm. You can define it that way. In this case, most of our problems with size would sort of disappear. But down the line, I feel that there's still, if there's interest, it's a weird question, so well, we're thinking about it. There's still a gap between the presented model and what really matters in reality. So we would like to do some fine-grained analysis and actually do this properly using numerical tests and things like this. So yeah, that's about it. I would like to thank you for listening for this talk, and all my collaborators who contributed to various parts of the stuff that I've been talking about. And a little bit of advertisement if you want to find out more about what we're doing in the Netherlands here, at least in around Leiden and Delft and Amsterdam. You can visit these links here. And I'm super happy to take whatever questions might have popped up that I absolutely did not pay attention to, I have to say.
Okay, Vedran, thank you for your talk. Let's clap a little bit. Of course, maybe I'm the only one with her mic on. Anyhow, so are there some questions right now?
I have a very tiny question. In one of your examples, you introduced something which you referred to as a cubic graph. What is a cubic graph?
Apologies, degree 3.
So I would call it a ternary graph, maybe, but okay, I understand.
Yeah, well, it's actually the title of the paper.
Okay.
Eppstein's paper is called, finding uncubic graphs, so you use that term. But yeah, the degree, the ternary graphs, sure.
Yeah. Okay.
Okay, does anybody else want to pose a question? Maybe one of the panelists. Maybe not. Okay, this is also okay. So because we are running a little bit late, so
yeah. Well, many thanks for the opportunity, and I know the talk was a little bit fast. Please, if you found anything interesting, feel free to email me at any point about anything. I'd be super happy to talk about this.
Yes, thanks, Vedran. Yeah, that's good. I think it's hard to, if you talk for 30 minutes and you want to cover some ground, it's hard to go very slow. So okay, so we will take a little break, and my watch is not running the same time as my computer, so it's 37. So I guess 5 minutes, and then we'll start again.